Very good afternoon to one and all present here. It is my honor and privilege to extend a heartfelt welcome to this esteemed gathering on the occasion of our 24th lecture of the Chancellor's Lecture Series. We are deeply honored by the presence of our respected dignitaries today. I extend a special and warm welcome to our chief guest, Professor Parameswaran Ajith, who has graciously accepted our invitation to grace this event and deliver the lecture. We are looking forward for an engaging and enlightening session. Now, I would like to welcome on the stage Professor Dharmeshwar Das, Chairman and Executive Director, Research, to give the welcome address.
Namaskar. At the very beginning, I extend on behalf of the Assam Downtown University our distinguished guest today for his valuable lecture on astronomy's new frontiers. We have invited Professor Parameswaran Ajith, who is a renowned astronomist, astrophysicist, and he is working in International Center for Theoretical Sciences in the Tata Institute of Fundamental Research at Bengaluru. We also welcome our Honorable Chancellor of Assam Downtown University in this occasion, and his presence will be very much inspiring to all of us. So I'd like to welcome our guest speaker for this 24th Vice Chancellor's Lecture Series. And I would just briefly give his bio sketch. Professor Ajith, his research is involved in the study of universe using the observations of gravitational waves. As a member of the LIGO Varga team, which has the collaboration with scientific partnership of researchers for multiple institutions worldwide, primarily in Europe, United States, and Japan. Ajith is the recipient of a special breakthrough prize in fundamental physics and the Gruber Cosmology Prize. Recently, he has been awarded UNESCO Task Kaza Center of Excellence Young Scientist Award for Frontier Sciences by the World Academy of Science, the Modali Award for Astronomy and Astrophysics by the Astronomical Society of India. He is a PhD from Max Planck Institute of Gravitational Physics, that is also known as Albert Einstein Institute in Germany. He is postdoctoral fellow in 2007 and 2008 in the same institute, and also postdoctoral scholar in the California Institute of Technology. Professor Ajith has been elected as the fellowship of the Indian Academy of Sciences. He is one of the reputed astrophysicists in our country and we are very fortunate to have him with us today for a lecture on astronomy, astrophysics. I would like to extend all our students here as well as faculty for this deliberation along with our Chancellor, sir. So I now request Dr. Benjamin Das to welcome him for the talk. Thank you.
Now I would like to request Honorable Vice Chancellor, sir, to felicitate Professor Ajith. Sir, Ajith, sir, please come on the dais for the felicitation. Thank you, sir. Now I request Ajith, sir, please.
Is that a permission issue? Okay. You can request, I need to request access. Yes. মাটি চুটকে কত চলিয়ে দেবো লাইভ তো মজা করে রয়েছে Yes. Hello. Can you do a full screen? Do a full screen. Control F. Yeah.
Full screen first.
Control L. Yeah. Is there a slide changer? Good afternoon. Can you hear me? Yes. Okay. Very esteemed colleagues and dear friends, I'm very pleased and very honored to give this talk here. And in the last couple of hours that I spent here, I came to know that starting from the Honorable Chancellor going to the students, there are a lot of interest in astronomy in this university. And I'm very pleased to hear that. And I've had a very wonderful chat with your Vice Chancellor also. And we shared some interesting thoughts of how astronomy, among other things, is a character building exercise also, something that Carl Sagan said. Even though, so I heard from your Vice Chancellor that instead of always looking down, one should always look up also sometimes to get a sense of our smallness in the universe. So I will try to bring up a complementary story of astronomy, and hopefully you'll get a sense of humility also by going through this. So, as many of you know, astronomy is the oldest of the modern sciences. It started about 400 years ago by this very humble instrument called the astronomical telescope. It was just invented by this gentleman, Galileo Galilei, who was an Italian polymath, who was an astronomer. He invented astronomy. He was a modern astronomy. He was a physicist, mathematician, a scholar of all kinds. Of course, the telescope was not invented by Galileo by himself. It was invented by other people. But Galileo was the very first one who used this telescope to point to the skies. And he drew very interesting conclusions based on these observations. These are actual photographs of the notebooks of Galileo. So unlike the modern times, there were no cameras that time, there were photographic plates. So he had to painstakingly take notes as well as draw sketches of what he have observed. And he, as you can see, is a remarkable artist also. These are the pictures of the moon drawn by Galileo, hand sketches. And he saw that unlike the modern, the dominant thought of those times, just the Greek philosophers, that moon was not a luminous sphere. It is actually a very imperfect sphere, just like the Earth, which has large craters, mountains, and so on. So you could see these very beautiful drawings of how light basically creates shadows in these craters, and Galileo could even measure the depth of these craters, etc., etc. These are what are the photographs, the drawings of what are called the Galilean moons. These are the satellites of the Jupiter, and I understood today that using the telescopes you have here, your astronomy club members have observed what we call the Galilean moons now. So you see these 4 satellites moving around the Jupiter. And this was actually a very big thing, because until then, at least in Europe, the Earth was considered as the center of the universe, and everything else was moving around the Earth. And this is the very first time in the history of human beings someone saw something orbiting around something else. So these satellites were not orbiting the Earth. They were actually orbiting something else, the Jupiter. It's already the first nail on the coffin of the geocentric theory of the universe. And here is something else. This is the telescopic observations of the planet Venus, which, as you know, is the closest planet around the sun. And by carefully observing this planet, Galileo saw that the Venus has phases just like the moon. The moon goes from a crescent shapes to a full moon over a part of 14 days or something. And the same thing happens for Venus also. So if you want to explain these phases of Venus, the only way of explaining the observed phases of Venus is by assuming that the Venus is actually orbiting the sun, just like the Earth, and not other way. If it was orbiting around the Earth, we would not have seen such phases of the Venus. So based on these observations, Galileo wrote a compelling treatise called The Dialogue of the Two Chief World Systems. Unlike the modern times where we write our conclusions as scientific papers, in those times people wrote their conclusions as big books. So it's one of the most important books in the history of sciences. So Galileo makes this book in a very entertaining way. There are 3 people. The one is a representative of the old geocentric world system, in which everything else is moving around the Earth, where the Earth is the center of the universe. And there is this new person who argues, based on Copernicus, his theory, that basically all the planets, including the Earth, is actually moving around the sun. And the third person, who is like a neutral referee or an umpire, who listened to both arguments and decided finally that the heliocentric theory, in which the sun is at the center of the universe, is more favored by all the observations. So basically these observations challenge the prevalent worldview of the times, and basically started this intellectual movement called the Enlightenment, which paved what is called the scientific revolution. So basically all the modern science that we see in the last 400 years and all the technology that came out of this essentially starts here. So these the instrument, these called astronomical telescopes, really made a huge impact in all our lives in the last 400 years. So that's one story. While the world was moving around with scientific revolution and all these technological changes, astronomers continued to do their business. And one thing was to make bigger and bigger telescopes. So why is it important to make bigger telescopes? Because if you have a bigger telescope, you can collect more light. Just like if you have a drizzle, if you have a big pot, you can collect more rainwater. This means that if you can collect more light, you can observe distant objects as well as fainter and fainter objects. So one very important person who made very important steps towards this is called a Dutch astronomer called William Herschel, as well as his sister called Caroline. It was not very well documented in the history of astronomy. So they made bigger and bigger telescopes. This is actually a sketch of the 48-inch telescopes, a telescope that's a 48-inch diameter made by the Herschel siblings, the Herschel's brother and his sister. As you can see, the size of a person is like this. And the telescope is really, the opening of the telescope is as big as the size of a person. So using this telescope, they made very interesting discoveries, including the planet Uranus. This is the first thing that you cannot observe using the naked eyes. But more interestingly, they tried to do, in particular, William Herschel tried to do some very audacious things. One thing that he tried to do was to actually count the number of stars in the sky. It's it's something that we see as an impossible thing to do, but he tried to do that. So people knew that basically we are part of a galaxy. And we know that we are part of a galaxy called the Milky Way. The galaxy has now we know that it's about 100 billion stars, 10 to the power 11 stars in the galaxy. And most of these stars are arranged on a disk. It's a spiral galaxy, so almost in a plane. And since we are part of this galaxy, we are seeing through this disk. So that's why it appears as a strip in the night sky. So if you're going to Arunachal Pradesh, for example, in a clear sky, you would see this strip, Ladakh, etc. Like this is the Milky Way. And Herschel knew this. So he tried to actually reconstruct a three-dimensional shape of the Milky Way by observing many stars. And this is what he got. He got something reasonably close to what we understand as the shape of the Milky Way right now. But he did make a mistake because he put the sun at the center of the Milky Way. See, as human being, it's very hard for us to get out of our sense of importance, right? That's why in the olden times, the Earth was the center of the universe and everything was around us. And Galileo and Copernicus and Kepler, etc., got rid of this idea and they placed the sun as the center of the universe and everything else is moving around the sun. So even Herschel could not get rid of this idea that sun is a very important thing. So he put the sun as the center of the Milky Way. But now we know that sun is just occupying a very unimportant part of the Milky Way. It's about 8 kiloparsec, 8,000 parsecs, about 27,000 light years away from the center of the galaxy. In fact, there is a very famous T-shirt. Some of the astronomy club members might know this. There is a T-shirt called showing the Milky Way galaxy and a point here. And it says, "We are here." So we are basically living in a rather unimportant part of the galaxy also. So anyway, so astronomers continue to build bigger and bigger telescopes. This is, in fact, one of the biggest telescopes that we have right now today. This has a diameter. It's called the Keck telescope. This is 2 telescopes here, and each telescope has about 10-meter diameter. They are bigger than this room. So you could see, if you look at this, the size of a car is here. So this is a car here, and this is many times bigger than the size. So these are the twin telescopes, and there are many other telescopes, a large Magellanic telescope, etc., etc. There's a VLT, very large telescopes, and now India is also part of an international consortium that is going to make a 30-meter telescope, which is basically a diameter of 30 meters. It's probably bigger than the width of this room. So astronomers are making bigger and bigger telescopes. And why? Because they want to see fainter and fainter objects and distant objects. But this is not the only thing that astronomers were trying to do. So this is, for example, using these bigger and bigger telescopes, we can basically make pictures of the universe. And this is, for example, how the universe looks in optical light, the light that we can see using our eyes. So this is the astronomers use a particular coordinate system in which the galaxy is basically the x-axis. This is basically the size of our galaxy. As I told you earlier, we are in a galactic disk, and we are seeing through this galaxy. So basically, we are looking through this galaxy in this x-axis, and this is all very, very far away. These are Magellanic clouds, etc. So here is one picture of what we would see if you look at the universe using optical light, which is light that we can see through our observations. But we know that optical light is not the only light that is there. And we had these ideas through Huygens and other peoples in the 18th century. So for example, if you pass a composite light through a prism, it will get dispersed as these multiple colors. They're called the Vibgyor colors. We get a spectrum of light. And this is, all of you must have done this experiment in school. But Herschel again did something more than this. What he did was he put a thermometer just a bit away from the red part of this spectrum, where there is no light. It is actually dark. But after some time, he saw that the thermometer is actually increasing its temperature reading. So he concluded that there has to be some light that is invisible, that we cannot see using our eyes. And now it's called the infrared radiation. And it's now very popular now. And for example, one could do this, this experiment using a very simple setup. You can take a cardboard box, put an opening here, and put a grating or a prism, and then you would see these Vibgyor colors, and you can put a thermometer, and after some time, you would see the thermometer increasing its reading. So, and now also we know that, in fact, this is very popular. Infrared thermometers are very popular in the last 5 years, all thanks to COVID, right? It has basically turns out that everything is actually emitting some radiation, and our body has about 37 degrees, 40 degrees Celsius temperature, and our body is emitting radiation in infrared, and that's why by reading this infrared radiation coming out of our body, an infrared thermometer can basically read our body temperature without touching. You can see it from, it is very popular in the last 5 years during the COVID. We also now know that basically all this light, infrared radiation or visible light, radio waves, gamma rays, etc., all part of what is called a spectrum of electromagnetic waves. They all electric and magnetic fields propagating at the speed of light. And there is an entire spectrum of radiation. The longest wavelength of radiation is called the radio waves. Slightly shorter version is called the microwave, which we use for mobile communication, etc. And then the shorter wavelength is infrared radiation, which we use for infrared imaging, thermometers, etc. Then there is this visible radiation, which our eyes happen to see. There is nothing specific about that. It's only just property of our eyes that we are sensitive to certain region of the electromagnetic spectrum, thanks to the biological evolution that we had to go through. Then the next lower wavelength is ultraviolet. Then the lower wavelength is X-ray, and the shortest wavelength radiation is called the gamma ray, etc., etc. And over the last century, we also have developed detectors that are capable of measuring all these different frequencies of electromagnetic radiation. For example, if you break your hand, you will go to a doctor and they will do an X-ray because it is able to penetrate through our body, but not so much through the bonds. And if, for example, for gamma rays are used for radiation treatment in cancer, etc., etc. Radio waves are used as for radio communication. Microwaves are used for mobile communication or microwave oven, etc. Ultraviolet is used for sterilizing things. So we have basically used detectors and basically generators of radiation for various kinds of purposes. Interestingly, astronomers also have used these detectors to look at the skies also. So it turns out that all these radiation actually naturally occurs in the universe. They are produced by different kinds of astronomical phenomena. And in the last century, astronomers have made telescopes that are capable of measuring these different frequencies of the electromagnetic spectrum. Here is, for example, this is the large network of radio telescopes, one of the largest in India, called the Giant Meter Wave Radio Telescopes, GMRT, located in Pune. Dr. Saikia used to work with them. So this is one of the biggest telescopes that we have made in India. This is run by TAFR, the National Center for Radio Astronomy. So you can see a car here, which is about 30-meter dishes, and there are about 100 such dishes located in a very large area of Narayangaon in Pune. And here is a telescope detector that is capable of detecting gamma rays. Unfortunately or fortunately, we have to go out of our atmosphere to detect gamma rays because our atmosphere basically act as a barrier that would not let the gamma rays pass. And here is an X-ray telescope, which is called Chandra, in honor of the Indian-American astrophysicist S. Chandrasekhar. And here is a microwave satellite, which is capable of observing radiation in the microwave frequencies. And using these telescopes, if you look at these skies, one would see very, very different picture of the universe. So here is, for example, the same optical sky that I showed earlier. This is what you would see if you look at the sky using an optical telescope and make a composite image of all the sky. But if you observe the same sky using a telescope that is capable of detecting microwave radiation, you see a very different phenomenon. This is called the cosmic microwave background radiation. This is the light coming from very, very early ages of the universe. Currently the universe is about 13 billion years ago. This is a light produced by the universe when it was only about 3 lakh years. So it's really a baby picture of the universe. And what we now know that using this observation, the universe started as a very hot plasma, which is what we call the part of the Big Bang theory, hot Big Bang theory. And the universe was extremely hot and dense, and matter could not stay in this form of atoms and molecules. They have to be in a state of plasma, charged particles. And the universe is basically filled this hot plasma with a remarkably same temperature. And wherever we look at the sky, we would see this radiation coming from all directions, the same radiation. But there is a remarkably same temperature, the radiation, but there are small fluctuations. So the fluctuations are 1 part in 1 lakh, 1 part in 10 to the 5. And there is these red regions are the slightly hotter regions of the universe, and these blue regions are slightly colder regions. And now we know, using a theory of cosmology, that these hot regions eventually became stars and galaxies, and these cold regions became the large voids between galaxies. So from this baby picture of the universe, we know how the universe evolved to form the kind of thing that we see now, the large galaxies, clusters of galaxies, etc. Similarly, if you look at the sky using an X-ray observatory, you see very different things. You see black holes accreting gas, and this gas heating up and producing X-rays. And these are all these X-ray sources in the sky. Similarly, if you look at the infrared radiation, you see something else. If you look at the radio wavelengths, you see something else, etc. So basically, these are all different windows to the universe. The phenomena that you would see by looking at one window, you cannot see by looking at another window. They're all very different views of the universe. And now, but all of those are basically different frequencies of the electromagnetic radiation. But in the last 50 years or so, especially the second part of the 20th century, astronomical observations using non-electromagnetic messengers also have become possible. So here is an example of what is called a cosmic ray shower. The cosmic rays are not electromagnetic waves. They are charged particles. They could be protons or nuclei of heavier elements. And they actually travel with speeds very close to the speed of light. They are highly energetic particles. And luckily, we have an atmosphere. Otherwise, these cosmic rays hitting our body can cause damage to DNA, etc. But luckily, our atmosphere is protecting them. But these cosmic rays basically hit some of the nuclei of the atoms in the upper atmosphere and produce a shower of secondary particles. And here is an artistic image of the shower of secondary particles produced by a cosmic ray. One cosmic ray, it's called a cosmic ray shower. And these are again an artistic image of some water tanks. They are some of the best detectors for detecting these cosmic rays. When these secondary charged particles go through these water, they produce a particular kind of light called the Cherenkov radiation, and this has been detected using these some detectors. And by detecting these, which water tanks detect these cosmic rays, you can reconstruct the arrival direction of these cosmic rays. And again, this is some of the pioneering work was done in India. Again, done by TIFR. There was a cosmic ray observatory in Karnataka in the Kolar gold mines, about a few kilometers underground. There was a very interesting experiment going on where they took the first atmospheric cosmic rays. And unfortunately, because of the closure of these Kolar gold mines, we had to TIFR had to stop these experiments. But some of the pioneer experiments was done by here. But again, these cosmic astronomy is a very flourishing field now. Here is such an observatory in Argentina called the Pierre Auger Observatory. Here they detected these water tanks, and they detected this what is called the ultra high energy cosmic rays. So these cosmic rays are a billion times more energetic than the most energetic particle that we can create in the laboratory. So I guess most of you know that the largest particle accelerator that we have is the Large Hadron Collider in Geneva. And these cosmic rays are a billion times more energetic than the highest energy particles that we can create in these Large Hadron Colliders. So, and here is a sky map of the cosmic rays, the ultra high energy cosmic rays detected by this Pierre Observatory. It's a slightly older plot. So all these these black dots are cosmic rays. They are these ultra high energy cosmic rays coming from one part of the sky. So it turns out that nature has some mechanism to accelerate these particles, the charged particles, to ultra high energies. If you have some sense, it's like 10 to the 18 eV, electron volts, for the physicists in the audience. We have not really an idea of what exactly is a phenomenon that is producing these ultra high energy cosmic rays. Some astronomers believe that this could be black holes accreting matter around us, and these charged particles get accelerated, get thrown away. Some astronomers believe that this could be produced by pulsars, these rapidly spinning neutron stars that has very large magnetic fields. Some astronomers believe that this could be produced in this what is called a gamma ray burst, which is a very bright and powerful explosion of massive stars. These are all possibilities, but we don't exactly know what exactly is producing these ultra high energy cosmic rays. Another example of these, but the point is that now we have some other way of observing the universe, not using electromagnetic waves. They are actually charged particles coming from millions of parsecs, millions of light years away. And here is another example of such astronomy that is not using electromagnetic waves. These are called neutrinos. Neutrinos are also subatomic particles, like cosmic rays, but unlike protons, they are not charged particles. And neutrinos are very elusive particles. They have very little interaction with anything else, so they pass through us. For example, the sun is a very powerful producer of neutrinos. So when we speak, there are trillions of neutrinos passing through our body produced by the sun, but we don't see it. So they don't interact at all. And here is an observatory called the Ice Cube. It is in the South Pole, in Antarctica. So this is an actual photograph. It is you see the tip of the observatory, but the actual observatory is about 2 kilometers down. This Antarctic ice is a remarkably transparent thing. So these people have drilled kilometer-sized holes in these Antarctic ice and planted several photomultiplier tubes that would detect very small amount of light. And when a neutrino crosses through this ice, again, just like when they pass through the water, they produce this so-called Cherenkov radiation. They produce Cherenkov radiation, which is detected by these photomultiplier tubes, and then you can reconstruct the arrival direction of these neutrinos. It's a remarkable instrument, and the last 10 years they have made very, very important progress. And here is again, just like the other plots, we have a sky map of the arrival direction of these high energy neutrinos. Again, we don't exactly know what is producing them. It is believed that things like collapsing stars could be producing these high energy neutrinos, but they are probably more energetic than what we need for these things. And these are actually very important and complementary to the electromagnetic observations. So for example, if you look at the sun, we see its light produced by the outer atmosphere, the outer sphere of the sun, right? The light is produced from the surface of the sun, while neutrinos are produced at the core of the sun. And if you want to see the nuclear reactions happening at the center of the sun, neutrinos are the way to see. So they contain very complementary information. It is like, for example, here, seeing something as well as smelling something. They are very different kind of senses. And now, in the last 10 years, we have yet another new way of observing the universe. And this is by observing what is called the gravitational waves. This is my particular area of expertise. And gravitational waves are ripples in the space-time geometry, something is very hard to imagine. The existence of gravitational waves was predicted by Albert Einstein over a century ago as consequence of his theory of general relativity. This is the most accurate theory of gravity that we have right now. So this theory states that any massive object would curve the space around it, as well as it would actually slow down the flow of time. So it creates a curvature in the space and time. And when any massive object move, like a binary system of two stars orbiting around each other, these space-time curvature creates fluctuations. So these fluctuations in the space-time propagates to the universe at the speed of light, and these are called gravitational waves. This is something very difficult to imagine, but it's something that we can actually measure. So when a gravitational wave passes through the Earth, they actually change the geometry of our space-time. They actually distort the space in a very, very minute way. But you can measure it using very large antennas called the interferometers. And here are the photographs of these two antennas called the Laser Interferometer Gravitational Wave Antenna Observatory, LIGO observatories in the USA. These are what are called the Michelson interferometers for the physicists in the audience. They are these L-shaped instruments. So each of these arm has 4 kilometer size. It's 4 kilometer by 4 kilometer. So these cars are very, very small. You can't see in the car here. So there are two such observatories in the US. One is in the northwest in the state of Washington, and in the southeast in the state of Louisiana. So this location is marked in the globe here. And when gravitational wave pass through it, the Earth, they make the arms of this interferometer a little bit longer and a little bit shorter by a part in 10 to the minus 18 meter. So it's like 1,000 times smaller than a proton. So it's extremely small disturbance it is creating. But using these very sensitive instruments, one can actually measure the passage of these gravitational waves. And since there are multiple instruments located across the globe, there are 2 LIGO interferometers, there's a third one in Virgo called Europe, you can make sure that they are actually produced by the same gravitation wave, because they have to be consistent across multiple detectors that are separated by thousands of kilometers. So in 2015, 10 years ago, they detected the first gravitational wave signal. So here's a plot of this gravitational wave signal that they have measured. So this is a LIGO observatory in the Washington state, the LIGO observatory in the Louisiana state. So this is a signal that they had discovered. So it's the x-axis is a time in units of seconds. So they last only for a fraction of a second, about 0.2 seconds. And this shows the amplitude of these fluctuations in the space-time geometry. And you can see a particular shape. They have it's like a sine wave with an increasing frequency. The cycle duration is decreasing and increasing amplitude. So this kind of signal is called a chirping signal. It's a very characteristic signal. This is produced by a motion of 2 objects orbiting each other, typically 2 black holes, producing gravitational waves. They come closer and closer and merge. They would collide to form a more massive black hole. And by studying this signal, we concluded that this signal was produced by the merger of 2 black holes, each weighing about 30 times the mass of the sun, in a very distant part of the universe, about 1 billion light years away. A very distant galaxy, and these gravitational waves have been traveling through this billion years and reached the Earth on 15 September 2015, and we detected it. So this discovery was very well appreciated and made headlines all over. And these 3 founding members of LIGO, Ray Weiss, Barry Barish, and Kip Thorne, were awarded the Nobel Prize in 2017 for decisive contributions to the LIGO detector and the observation of gravitational waves. This is not the only signal that LIGO detected. 2 years later, another remarkable signal was discovered again by LIGO and Virgo. See this very, very characteristic shape here. And again, this was produced by, again, orbital motion of 2 neutron stars. Neutron stars are very exotic objects. They are produced at the end of the collapse of massive stars. They are produced by, they are extremely dense objects. They can be as massive as the sun, but their size only 10 kilometers. So they are basically a soup of neutrons. One thing that if you take a spoonful of matter from a neutron star, it would weigh more than the Himalayas. So it's an extremely dense object. And these this produced by the motion of 2 neutron stars. So you can see it's very clear track here. And most importantly, soon after this, we detected the gravitational signal. Several astronomical telescopes also observed a flash of electromagnetic radiation coming from the same part of the sky. So what must have happened is that this collision of these neutron stars also produced an explosion of nuclear matter, which produced a bright flash of gamma rays called the gamma ray burst. So this is the location of where we localize the gravitational wave, and this Fermi detector, which is a satellite detecting gamma rays, basically detected gamma ray burst also. And then a large number of optical telescopes and radio telescopes and X-ray telescopes looked at the part of the sky and produced this a spectrum of electromagnetic radiation coming from this exploding source. This is a very remarkable discovery because the first time we are seeing the same phenomenon, the collision of neutron stars, using multiple messengers. We see the electromagnetic waves coming out of it. We also see the gravitational waves coming out of it. And as I said, they contain very, very different kind of information. And by combining this information, we could do a lot of very interesting science, which is a test whether Einstein's theory is a correct theory of gravity. We could understand some of nuclear physics. But maybe for some audience, one interesting thing is that we now understand where the gold comes from. So have you ever thought of how various elements in the universe came out? It turns out that in the very first few million years of the universe, there was only hydrogen and helium. All other elements like the carbon, nitrogen, oxygen, that's all we are made of, they all synthesized inside stars through a process called nuclear fusion. So the hydrogen gets basically fused to produce helium, helium produces for heavy elements, etc., etc., etc. So you could form elements as heavy as iron inside stars. So when these stars then explode, all these elements get thrown away, and then again they form some other planets, etc. That's how life basically formed. But it turns out that elements heavier than the iron could not be formed through this nuclear fusion. But we see the elements here. We see gold, we see platinum, we see all kinds of uranium, plutonium, etc. in the universe. Where did they come from? So the astronomers had earlier thought that they could be produced in exploding stars called supernovae. But later observations suggested that there are not enough supernova explosions happening in the universe to explain the observed abundance of these heavy elements. Then this idea that they could be produced in the merger of neutron stars became popular. And for the first time, by observing this electromagnetic radiation from this merger, one could conclude that many of these heavy elements that we see in the universe are indeed produced by the merger of neutron stars. So in fact, this one particular merger must have produced an Earth mass worth of gold. It's a bit far away. It's about 100 megaparts, 100 million light years away. So you have no hope of getting this gold out of this. So again, this is not the only source that you observed. In the last 10 years, we have observed about 300 such gravitational wave signals coming from different parts of the universe. They all produced by the mergers of black holes or neutron stars. There is a cartoon that's showing all these black holes that you observe through these observations, not very important. And a large amount of very interesting science has come out of these observations in the last 10 years. Where are we heading to? In the next 5 minutes, I will say a little bit about what the future of this astronomy is going to be. One very important thing about these gravitational wave observatories is that using a single detector, we cannot tell where the signal is coming from. It's like if you have only one ear, you won't be able to locate the origin of sound. Right? We are able to locate the origin of sound because the sound would arrive at our ears at slightly different times, and our brain can basically triangulate the origin of the sound because the delay of the arrival of sound at these two different ears. The same way, if you have multiple detectors located at different parts of the world, this same signal would arrive at the detector at different times because gravitational waves travel at the speed of light. And using this time delay, we can localize the source in the sky, just like an owl can basically triangulate its prey using these two ears. So that's why it's important to have a network of detectors across multiple parts of the globe. And there are two LIGO detectors in the US. There's a Virgo detector in Italy. There is a small one in Germany where I did my PhD. It's a small one. And there is a fourth one coming up in Japan called Kagra. But most importantly for us, there is a third LIGO observatory coming up in India called the LIGO India. This is located in Maharashtra in the Hingoli district, in this village called Aundh. This proposal was submitted in 2010, but after several delays, we have now finally started construction of this project. It will be operational in the next 5 to 6 years, hopefully, and it will be a major contribution to the international network of gravitational detectors. It's a very exciting opportunity because it will significantly improve our ability to localize the sources of gravitational waves, and hence will enable the follow-up of these signals using electromagnetic telescope. More interestingly, it's a multidisciplinary, very challenging project. It involves a lot of cutting-edge technology in different aspects of fundamental science as well as engineering. It involves a cutting edge in mechanical isolations, in optical systems, lasers, material science, computing. So it has a whole variety of challenges across the different kinds of domain. And I hope that some of the very aspiring and smart students would contribute to these very cutting edge aspects, both in fundamental sciences as well as in technology. There are also ongoing plans to build the next generation of detectors, which will improve the sensitivity by a factor of 10, some going underground, etc. But also, there are, just like the electromagnetic waves have an entire spectrum, starting from radio waves all the way up to high frequency gamma rays, gravitation waves also have an entire spectrum of frequencies. And so far, we're only observing a small part of the spectrum of gravitation waves. There is the upcoming space-based detector called LISA, which will detect lower frequency gravitational waves. And there is an intermediate, there are ideas of using the moon itself as a detector of gravitational waves, detect intermediate frequencies, etc. So just like we have a spectrum, I showed the spectrum of electromagnetic radiation. There's a whole spectrum of gravitational radiation, and the longest wavelengths could be as large as the size of the universe. And in the next few decades, we will have detectors operating at all these frequencies of electromagnetic radiation and bring up an entire combined picture of a large number of very interesting phenomena. So let me stop here. The summary is that the modern astronomy began about 400 years ago with the discovery of the optical telescope. In the last century, basically, we have expanded the astronomy into different frequencies of the electromagnetic radiation. But especially in the last century, we also have used non-electromagnetic messengers like neutrinos and cosmic rays to study the universe. The latest weapon in the astronomers' arsenal is the study of gravitational waves. Just started in the last 10 years, and we have already detected about 300 gravitational signals so far, and we will be detecting thousands of new signals in the next few decades, really opening up a new branch of astronomy. And in particular, for the Indian community, the exciting news is that the new LIGO detector is coming up in India, which presents a lot of both technical as well as fundamental science challenges. It's also an opportunity for Indian scientists and engineers, and something that we hope to contribute to this frontier of astronomy in the next decade. So let me stop here, and thank you very much.
Thank you, sir. Thank you, sir, for enlightening us with the astronomy's new frontiers. Now the mic is open for everyone if anyone is having any doubt, like if they want to ask some questions. Yeah, sir.
It is an estimate, yeah. Yeah. No, it's an estimate. It's not an exact number. Yeah, it is like.
And another, the radius from the sun is
neutrinos.
Yes.
Ah, yes, yeah.
So neutrinos is a radius of.
Yeah. No, that's it. The neutrinos are small particles, but as we speak, there are trillions of neutrinos are passing through us, but they don't interact with anything.
But other radiation from the sun is harmful.
I mean, things like there are X-rays, etc., from the sun, which could be harmful, but our atmosphere is protecting us. Yeah, yeah, yes. No, this is not harmful. Yeah. It is not sitting inside the atom. It's always free. It's always passing through it. So, for example, when you combine an electron and a proton to produce a neutron, it also produces neutrino. It doesn't sit. It always travels.
In the cosmic ray, we found that the gamma ray is not related with the atmosphere.
Yeah.
So gamma ray has any effects, where they affect on human.
Yes, gamma rays can damage DNAs, etc.
Utilize this gamma ray for the benefit of the human.
It is already used. It is already used for radiation treatment and so on. So when you have a cancer radiation treatment, yeah. Yeah.
Gamma ray, but
Yeah.
in the radiation treatment is that it is the alpha beta particles.
Yeah.
Beta particle is more selected than the alpha particle.
Yes.
Okay.
Yeah.
Gamma has no such effect, I think.
So alpha particle is just a helium nucleus. It's a particle, while gamma rays is basically a quantum of light. It is a high energy radiation. It is already used for.
That gamma ray radiation emitted through this galaxy, star of the galaxy, or the sun.
Both, but they are all very weak. For the treatment, we also have sources of gamma rays. We create gamma rays on the lab also. For the cancer treatment, etc., we create our own gamma rays for the treatment.
So this is also the radiation.
Yeah.
So can you generate the energy from?
Yeah, you can create gamma rays. Yes.
Thank you.
Any more questions? Sir, why do you use the deep mines like gold mines to detect cosmic ray? If the cosmic ray shower is happening in the upper atmosphere, so why do you go that deep?
Yeah, it's interesting. The deep mines are useful for detecting neutrinos, not cosmic rays. The reason is that cosmic rays create a background, a noise for detecting neutrinos. So, however, if you go deeper in the mine, the cosmic rays get absorbed by the Earth, but the neutrinos would pass through everything. That's why to study neutrinos, you have to go underground. But again, even for study cosmic rays, also some background particles need to be avoided. That's why certain underground facilities are useful for cosmic ray studies also. But most of the cosmic ray detectors are on the surface, but the neutrino detectors are underground.
I have another question. If cosmic rays are available at upper atmosphere and you can detect them and measure them, then is there any way to use it as a source of energy? Because you told that the highest energy that is emitted by cosmic ray. So right now we have a world where we have less renewable energy coming, so we have to talk about energy sources. So can cosmic ray be used as source of energy in future?
Unlikely. The reason is that even the individual cosmic rays are very highly energetic. There are not many of it. There are not as many of them. So there's a flux of radiation is not very high.
So first of all, it's a wonderful presentation, sir. Sir, I have a small question. Sir, as you have mentioned that when two black holes come closer or collide, that generates gravitational wave, or it's create fluctuations in the space-time. So, sir, our all communications from satellite, is it disturbs that fluctuations? Is it disturbs our communication systems, like from Earth to that satellites and other objects?
Not really. The reason that these fluctuations are extremely tiny. Even to measure these fluctuations, you have to have this kilometer-sized instrument. So they have no practical effect on other things yet. Once we have such sensitive communication devices, they might play a role, but not yet.
Thank you, sir.
Any more question?
Okay. Maybe the last one. Yeah, yes.
So, Professor Parameswaran, actually one day I read in the newspaper that star will swallow the planet. I told my 8-year-old granddaughter, she clutched my hand. So we shall be swallowed.
So the star is swallowed by a planet.
Star will swallow the planet. Then it is written in the newspaper that 2 million years hence. So she was very happy that not now.
Yeah.
Now I have got one question, actually astrology.
Yeah.
astronomy and astrology.
Yeah.
You may not know about astrology, but from our experience, from our birth and everything, astrology is also Navagraha. There is a temple, 9 planets. I don't know when it was started. So how did all those people knew about 9 planets?
Actually, in astrology, Navagrahas are different from the 9 planets that
I
we
know.
know.
No, let me tell you a very true story.
Yeah.
When I was born, there was a astrologist who came and made my horoscope. Then this is a true story. Then the horoscope said that Saturn is on my head. Then I was in a medical college, working there. Then I was the only eligible person to become associate professor. For 3 years, I was not given the job. Then my mother-in-law came, she said that you take the horoscope and go to Navagraha. And Navagraha, one fellow said that Saturn is not allowing to become professor. So what should you do? That you have one red flower, 1 meter of red clothes, and some foreigners only. And come to Navagraha, give a puja. Would you believe that after the puja was over at 1 o'clock, I got a phone call from Shillong that minister has signed the file. So these are pure experience of my life. I thought you will show the whole universe in one slide, but whatever you said is really interesting, but not for us. Thank you very much. But who created the universe?
Yeah, so let me ask, give you my take about the astrology. It's an easier question to answer. It's a very interesting thought that our time of the birth would determine our fate, right?
Yeah.
And there are many studies have done to see if there is any merit in these predictions. I'll tell you one thing. Probably the most, now we are talking about Professor Narlikar. Professor Narlikar himself has conducted a very interesting study in collaboration with several astrologers in Maharashtra. What he did was something. He took the horoscopes, some of the best school children in astronomy, the rank holding children in schools in Maharashtra. He also took about the same number of horoscopes for special children. They are mentally challenged children in Maharashtra. So if their horoscopes can predict their mental abilities, an astrologer, by looking at their horoscope, should be able to decide whether there's a horoscope of a golden child or a mentally challenged child. And he invited many astrologers in Maharashtra to participate in this competition. And this is blinded. You're a doctor. For example, if you have a new medicine, the question is whether how do you determine its effectiveness, right? There people do a double-blind study, because a new medicine could accidentally cure something, or it could be something that is actually because of its chemical reaction. Because there's what called placebo effect. And sometimes the fact that we have some hope in a medicine would cure us. So what the doctors do is they do a particular double-blinded test. For example, they administer a real medicine to half of the patients, and real medicines, this fake medicine, placebo, to half of the other patients. And to whom the real medicine is given is blinded by to the doctor as well as the patient, because we don't have a bias system. The question is, at the end, if the medicine has some real value, a larger fraction of the patients administered the real medicine should have a better curing rate as compared to the placebo. So the same study was done for astrology. There are several studies done in astrology. For example, this thing that Narlikar was done was to compare, predict whether this horoscope is from a special child or a rank-holding child. And none of the astronomers were able to do that, apart from statistical fluctuations. There are many such studies. So, we all have our personal experiences, and we are likely to believe certain things. But if you look at a large amount of study, which is a scientific thing to do, unfortunately, there is no evidence that astrology has any predictive power.
But how the astrologer who actually had made my horoscope, he knew the Saturn. Saturn was sitting in my way. So that is how did he know about Saturn? Navagraha, 9 planets are there.
it's an interesting system of measuring
Interesting.
time.
So
more than
how,
that.
I wonder, how did the astrologists, they are not very learned scientists or anything, but their horoscope, in my case, it came out to be true.
Yeah, see, we all have our personal experience, which could be slightly peculiar, but if you do a systematic study, there is no evidence that astrology has any predictive power.
Mine was miracle. I completed the puja. After that, I got the news.
Yeah.
Okay, thank you, Professor.
Since we are short of time, okay, one more question. So one more question. Last question. Since we are short of time, one last question. Ajith Kalita, sir. Okay, done. No more questions? Okay. Okay, I would like to request Honorable VC sir for giving his concluding remark.
Thank you so much, Professor Parameswaran. Actually, concluding remark at the end of a beautiful talk is given by experts. Like most of, like as you know, the audience particularly, I have already had a discussion before coming here with Professor Parameswaran, gave him a background, but some of you, the students, you may be young, we have a telescope in J block. Somebody asked me that why we have purchased a telescope, not to talk about astronomy. We don't have a physics program in this university. And when we organized this lecture, somebody asked that we do not have any experts, and like generally you do the intellectual exercise you do among peers who does research or study in same field, but Professor Parameswaran has come on our request to deliver a talk on a topic or in the area of study, knowledge, which we don't have anyone here. But the interesting thing is, when I purchased this telescope install, 250 students, some of them are from your, this, what subject we had a discussion before this meeting in my room. Forensic science. There are 10, 12 students from forensic science, students from engineering, students from other subjects of biology. What is like they have enrolled and they do regular sighting of the events happening in the sky. See, like about knowledge, we are not yet certain about anything. This is a systematic way of pursuing our curiosity. This is what science constitutes. And he's also said the astrology and astronomy, maybe at some point of time India had like knowledge. Like people say Einstein, a lot of things, like those who have read about Einstein biography, he says he do a lot of things in his brain only. People talk a lot of things, even see Galileo, without any your camera, he could draw a picture of moon. Like they're extraordinary people. It's a gift of maybe this Almighty. We still believe in some superpower, right? So they have extraordinary power and has, through their curiosity, has enhanced our curiosity, right? I hope today, through the lecture, many young minds here have got a lot of things to take home. At least this lecture will make us humble. The purpose with which I wanted to install a telescope, requested the management, they readily agreed, is that we should all try to see towards the sky, up. It helps you remain humble. It adds to our humility. It helps us to grow in, like, enhance our like, we have to be humble, right? Rather than seeing downward, we should see downward, we should see upward. Like, there's no end in every discipline, like any other discipline. The human intellect is trying to see the absolute truth or ultimate truth. Maybe astrology also wanted to do some point of that, but we have lost it. But we could not compete with the modern science. Since the origin of astrology is India, I am also inviting young people. They should think, somebody like, why, like Sir has said, his horoscope work, like maybe many people horoscope works. Maybe those astrologers, their ingenuity, their level of intelligence and their skill, like some of them are highly like skillful, they could predict certain things. So we'll not summarily negate astrology. There is, you can ponder over, who knows, somebody like may bring something great things. But what Professor Parameswaran present is the humankind systematic so-called scientific methods through that which can be repeated by others, that which is the essence of science. If it is not repeatable, it is not science. That's it. So astrology has failed to compete with astronomy because we have not been able to show its repeatability. Now, this is just for the young people, but you can challenge. Why not? It should be repeatable. I'll take it up. There's no harm venturing into any branch of study, but it has to be in the context of what we do by science globally. That should always be in core of our thought and in our heart. With these words, again, once more, thank you all for coming to this seminar and listen to this beautiful talk. And once more, Professor Parameswaran, I hope we'll be able to, as I told you, with Dr. DJ Saikia and people, astronomy people in Guwahati University and some other few institutions in this region, maybe we can organize something more in the future. And I hope you will readily agree if we invite you again to this university. Thank you very much.
Thank you, sir. Now I would like to request Dr. Dhruva Sharma for giving the vote of thanks.
Good afternoon to one and all. It's my privilege and pleasure to stand before you to offer this vote of thanks on behalf of the organizing team of the Chancellor Lecture Series. First and foremost, I would like to extend my heartfelt thanks to our distinguished speaker, Professor Parameswaran Ajith, the Dean, Programming Activities, ICTS TIFR Bangalore. Sir, your lecture on astronomy's new frontier was not only informative but thought-provoking. We are grateful for the time, effort, and the expertise you share with us today. I would like to express my gratitude to our Honorable Chancellor, sir, whose inspiring vision and unwavering leadership always ignite our path. I offer my sincere thanks to our Honorable Vice Chancellor, sir, for his able guidance. Sir, your commitment to fostering intellectual growth and providing a platform for engaging dialogues is something that we truly appreciate. A big thanks to Professor Dharmeshwar Das, Chairman and Executive Director Research, for his continuous support and guidance in organizing this event. Thanks to all the deans of faculty of study, all faculty members for their valuable time and support. Thanks to all our participants, attendees. Thanks for your active involvement and enthusiasm. Last but not least, thanks to all our organizing team, volunteers, and everyone behind the scene whose hard work and dedication made this event success. Thank you once again.
Thank you, sir. Now I would like to call on the stage everyone for a group photo, sir. Yeah. Yes.